Hello everyone. In this lecture, we are going to discuss about the velocity analysis of a 6-bar link. In this question, a toggle mechanism is shown in the figure. The dimension of the figure is given. All the dimensions are in millimeters. Find the velocity of the points B, C, and the angular velocity of links AB, BQ, and BC. In this particular mechanism, link OA is the crank. This mechanism consists of 6 links. C is the slider. The crank is rotating in the clockwise direction, and if you consider the motion of each link, we know that the crank OA will rotate in the clockwise direction. It is having a purely rotational motion. Similarly, the link BQ, where Q is the fixed point, also will undergo a rotational motion about Q. The slider C will have a translatory motion along x-axis. The other two links, that is link BC and AB, will have a general planar motion, that is a combination of rotational and translation motion. Here in the question, it is given that the crank is rotating at an angular speed of 50 revolutions per minute in the clockwise direction. So we will proceed with the question. To start with, we have to draw the line sketch of the mechanism using the exact dimension. So using the compass, pencil and scale, you can draw the mechanism. Okay, I want to remind you that you have to draw according to the dimension. Here all the dimensions are given in millimeters. So for example, if you are drawing the crank is having a unit of 30 millimeter. So it can be equated to 3 centimeters. Okay, so with 3 centimeter length, you can draw the crank OA. Similarly, the other links. Okay, so to draw this mechanism, you have to use compass also. So using those instruments, you have to draw the mechanism. After drawing the line sketch of the mechanism, we need to start drawing the relative velocity diagram. So to start with, we have to take the driving link. The driving link here is link OA. We can represent the velocity of A relative to O. To find the magnitude of velocity of point A relative to O, in the question, the speed of link AO is given. Using this, we can find the angular velocity of A relative to O, that is given by 2 pi into n by 60. Once you get the angular velocity of link AO, you can find the magnitude of velocity of A relative to O, since we know that point A in link AO will undergo a circular motion. So velocity of A relative to O can be found out by r into omega, where r is the radial distance, or otherwise the length of the link, OA into omega OA or AO. Okay, so from this you can find the magnitude of velocity of point A relative to O. That is what I have found here. You will get the magnitude of velocity of A relative to O as 0.157 meter per second. Now we need to determine the direction of velocity of point A relative to O. In the question it is given that the crank is rotating in the clockwise direction. So the direction of velocity of A relative to O will be tangential to the path traced by point A. And we know that since link OA is undergoing a circular or a rotational motion, point A will undergo a circular motion. That means the direction of point A relative to O, velocity of point A relative to O will be tangential to the curve at that point A, or it is nothing but the direction will be perpendicular to link OA. And since the link is rotating, or the crank is rotating in the clockwise direction, the perpendicular direction will be towards right. Okay, so what is shown in the figure will be the direction of velocity of point A relative to O. So what you do is, from point A you draw a line perpendicular to link OA in the upward direction. Okay, now since now we have found out the magnitude and direction of velocity of A relative to O, now we have to locate it in the velocity diagram. To start drawing the velocity diagram, first we need to locate the fixed point in the mechanism. As we have done in the previous question, it is better that you orient your notebook horizontally, and at the top surface or the top region of the page you can draw the line sketch of the mechanism, and below the line sketch of the mechanism you can draw the velocity diagram. So at some point below the velocity diagram, some point below the line sketch of the mechanism, you can locate the fixed point. As I have told you, the fixed point in this particular mechanism are point O and Q. So what you do is, at some point below the line sketch of the mechanism, you locate a point and designate it as O, Q. That is small letter O, Q. After locating the fixed point, now we need to draw a line from the fixed point, that is O, Q, such that that line is parallel to the direction of velocity of A relative to O. That means the line will be something like this. Okay, the length of the line will be the magnitude, and we have got the magnitude of velocity of A relative to O as 0.15 something. So if you represent that length here in the velocity diagram, it will be very small. Okay, so what you can do is, you can multiply the magnitude with a scale factor, let's say some 10 or 20. Okay, if you multiply by 10, it will become 1.5 something. So that length can be taken as the magnitude of velocity of A relative to O. Okay, that means we are going to scale we are going to scale up the velocity diagram. That is what I have drawn here. Okay, so this represents the velocity vector of velocity of point A relative to O. Okay, so please note the designation also, and also the arrow. So those details I have already specified in the previous video. Now we will move on to the next link. The next link is link AB. We know that link AB is having a general planar motion, but for representing its motion in the velocity diagram, we make the assumption that link AB is having a pure rotational motion, and we assume that the link is rotating about A or about B. Okay, and regarding the velocity of point B relative to A or A relative to B, we don't know the magnitude and we don't know the direction. But only thing that we know regarding the velocity of point B relative to A or A relative to B is that the line of action of that velocity will be perpendicular to link AB. So what you do is, from either point B or from point A, okay, you draw a line perpendicular to AB. Okay, so that is what I have drawn here. This line represents the line of action of velocity of B relative to A or velocity of A relative to B. Either thing will be the same. Okay, so what you can do is you can extend this line beyond B also. Okay, and now what you do is, here in the velocity diagram here, you have point A. Okay, so what you do is, from point A you have to draw a line parallel to this line of action. Okay, so from A you draw a line parallel to this line of action. You can extend that line on either side of A. Okay, so that is what I have done here. Okay, so this is the line that I have drawn from A, which is parallel to this line of action of velocity of B relative to A. Next we will move to the next link. The next link is link BC, that is this link. So before that, we know that you have a slider at C, and we know that the slider will have a reciprocatory motion along x-axis, that is along positive, that is the slider can move along positive x and negative x. Okay, and the motion of the slider will be relative to the fixed point. So the fixed point will be is O and Q. Okay, and regarding the motion of the slider, we don't know the magnitude of velocity of the slider, or we don't know the direction also. But one thing that we know is the line of action of velocity will be along x-axis. So what you do is, from point O you draw a line parallel to x-axis. Okay, so from point O you draw a line parallel to x-axis, and then you can extend the line be about O and Q, on either side of O and Q. Okay, so that is the line I have drawn here. Now we will move to link BQ. You can select link BC also. Okay, but at that moment when I drew the velocity diagram, I selected BQ after the slider. Okay, now regarding regarding link BQ, we know that Q is a fixed point. Okay, so that means link BQ will have a rotational motion. Okay, even if it is a oscillating motion, it will be a rotational motion about or an angular motion about point Q. So regarding the velocity of B relative to Q, we don't know the magnitude and we also don't know the direction. But what we know is the line of action of velocity of B relative to Q will be perpendicular to link BQ. Okay, So what you do is, from B, you draw a line perpendicular to BQ. That is this line. And this line represents the line of action of velocity of B relative to Q. Okay. So what I have written here, BQ or QB. This QB is wrong. Okay. Because anyway there is no relative motion between Q and Q relative to B, because Q is fixed. Okay. So for link BQ, it is always B relative to Q. Okay. And the line of action will be perpendicular to link BQ. So in the velocity diagram, what you do is you have point Q here. Okay. From Q, you draw a line parallel to this line. Okay. From Q, you draw a line parallel to this line. Okay. So that it will be something like this. You can draw that line beyond Q also. Okay. Beyond Q and beyond this line, you can extend. Okay. So that is what I have drawn here. So this line is the line that is parallel to the line of action of B relative to Q, and that line will meet the line from A, and that meeting point will be B. Okay. You please note how the designations are made, how the directions are indicated, and based on that direction how each velocity is designated. Okay. So the method we have already discussed in the previous class. So you please, if you have any doubts, you please refer those videos. Now we will move to link BC. Link BC undergoes a general planar motion. So like link BA, here also in BC, we assume that it undergoes a rotational motion. So the link can rotate about B or C. Okay. That means you can represent velocity of B relative to C or C relative to B. Okay. Regarding the velocity of B relative to C or C relative to B, we don't know the magnitude, and also we don't know the direction like the previous links. But we know that the line of action of velocity will be perpendicular to link BC. So what you do is, from C or B, you draw a line perpendicular to BC. That is what I have drawn here. I have drawn a line perpendicular to BC from C. Okay. So this line will represent the line of action of velocity of B relative to C or C relative to B. Now in the velocity diagram, we have point B. Okay. So from point B, you draw a line parallel to this line. Okay. So it will be something like this. Okay. So that is what I have drawn here. So this line BC represents the line of action of velocity of B relative to C. Okay. So that line will meet the horizontal line from OQ at point C. Okay. So now we have completed the velocity diagram, and you please mark all the velocities as I have marked. Okay. This is the enlarged view of the velocity diagram. So please see or observe how the directions are marked and how the designations are given according to the direction. Okay. So regarding the way in which these directions are given, you please refer the previous video. Okay. Now in the question, you have been asked to find the velocity of point B and velocity of slider C. And these velocities have to be taken with respect to the fixed point. Velocity of B is relative to fixed point Q, and the slider will be based on fixed point O. To find velocity of BQ or velocity of B relative to Q, you need to measure the length of the line BQ in the velocity diagram. Okay. Similarly, to find the velocity of C relative to O in the velocity diagram, you have to measure the line OC or CO. Okay. And again, I am reminding, when we started drawing the velocity diagram, we had the magnitude of velocity was multiplied with a scale factor of 10. So when you take this measurement has to be divided by 10. Then only you will get the exact magnitude of velocity. So for me, the velocity of B relative to fixed point Q is obtained as 0.14 meter per second, and velocity of C relative to O is obtained as 0.11 meter per second. Next, we need to find the angular velocity of link AB, BQ, and BC. To find the angular velocity of AB, we assume that link AB is undergoing rotational motion. So in that case, we can write the linear velocity of A relative to B or B relative to A can be written as R into omega, where R is the length of link AB into omega. Omega is the angular velocity of link AB. Okay. So to find angular velocity of link AB is obtained as velocity of A relative to B or B relative to A, so that I am not writing, divided by the length of the link AB. From the velocity diagram, you can find what is velocity of A relative to B or B relative to A. That is, it is the length of line AB in the velocity diagram. That has to be divided by the scale factor of 10 and then divided by the length. You get the angular velocity of A relative to B. Similarly, you can find the angular velocity of BQ and BC. That is what I have found out here. You will get the angular velocity of AB or BA as 0.75 radians per second. Angular velocity of BQ as 1.4 radians per second, and angular velocity of BC as 1.35 radians per second. As I have told you, there may be slight variation in the answers that you have got. That is because of the accuracy, based on the accuracy in which you have drawn the line diagram of the mechanism as well as the velocity diagram. Okay. Thank you.